So, hi everyone, I'm Hongyi Zhang. I'm going to talk about our work in an estimate sequence of geodesic convex optimization. This is joint work with Suvrit. So, in data science and machine learning, many optimization problems in vector space have structured nonlinear constraints. And for example, we have principal component analysis and fixed low rank matrix completion, as well as covariance matrix estimation. And remarkably, these problems, if we consider their specific geometry, they can be viewed as unconstrained problems on Riemannian manifolds. So Riemannian optimization gives us a unified view for these problems, and sometimes they can provide additional, reveal hidden properties such as convexity as well as symmetry. So how does Riemannian optimization algorithm work? It works by generalized operations from vector space to Riemannian manifold. For example, exponential map generalize vector addition by map points from the tangent space onto a manifold. And inverse exponential map maps generalized vector subtraction by map points on a manifold to a tangent space. We can also rigorously define lengths, angles, differentiation, and vector translation on Riemannian manifold. So, and function classes can also be generalized. For example, we have on Riemannian manifolds functions that are geodesically convex, geodesically Lipschitz, geodesically strongly convex, and geodesically smooth. Here, let's give a closer look at geodesically strongly convex function. Gx here is the Riemannian gradient which lives in the tangent space of x, and the inverse exponential map of y at base x also lives in x tangent space. Also note here that the inner product and the norm are defined with respect to the Riemannian metric at x. However, what makes Riemannian optimization special is metric curvature. So, for example, if we imagine we move on these different surfaces using the same steps, we may end up with traveling different distances. So, but the good thing is, it turns out that what matters is this sectional curvature, which is the simplest curvature definition we can have on the Riemannian manifold. Basically, a sectional curvature is the Gaussian curvature of a two-dimensional submanifold at a given point. Previous studies of iteration complexities of Riemannian optimization include gradient methods, stochastic gradient method, and fast incremental gradient methods. So these are work by our group as well as Kasai et al. And there are alternative study by Bomo et al. On Riemannian gradient descent and trusted region methods, which they baking sectional curvature into the Lipschitz assumption on the pullback function. So in this work, we study Riemannian Nesterov's momentum methods. And we also note that a recent work by Liu et al. Proposed accelerated gradient methods. However, they assume that they have an exact nonlinear solver oracle, which in practice may be intractable. So let's go into our algorithm and analysis. We make the following assumptions. The domain X is a geodesically convex set with where both the exponential map and its inverse are well defined. And F is geodesically L-smooth and mu-strongly convex in X. The sectional curvature in X is bounded by K. And we assume the f assumes its minimum in X, and all the iterates remain in X. So the algorithm works like this. First, we have iterate vk and xk, and we find yk by interpolation. The right figure shows what happens in yk's tangent space. The next step, we make a gradient descent step from yk to get xk plus 1. In the next step, we extrapolate vk and xk plus 1 in yk's tangent space to get vk plus 1. So our analysis make use of the estimate sequence technique proposed by Nesterov in his landmark paper in 1983. First, we define the delta phi as the gap between phi and f's optimal value. Then an estimate sequence of f is defined as a pair of sequences phi k and lambda k, where lambda k goes to 0 and phi k is always upper bounded by lambda k times phi 0, delta phi 0. So with the definition, let's see how it works in vector space. In vector space, we start with phi k like this, and we can construct a phi k plus 1 by a convex combination of phi k with the quadratic lower bound of f. Then it turns out that by the specific update of Nesterov's method, we can first have this estimate sequence convergence, and then we can also show that the function fx is also upper bounded by this estimate sequence. So which gives us a proof of acceleration if we choose a good alpha. Then how does it work on Riemannian manifold? We can start with the same construction of phi k, and then construct the phi bar k plus 1 by convex combination of phi k with the lower bound on f. So everything seems to be going well. We have this shrinking of delta phi k. We also have an upper bound of f by phi. However, here comes the problem. We find that your construction of phi k plus 1 and phi bar k plus 1 will have different form. Especially if we look at what happens on a sphere, then we realize that the squared norm of these two formula, they live in different tangent spaces. So they do not equal. Then what we do is that we find, although that these two quantities do not equal, we can use tools in differential geometry as well as analysis to give a multiplicative bound on the difference, which depends on the sectional curvature upper bound, as well as bk plus 1 here is the distance from the iterates to the minimizer. So with this, we have enable a new valid sequence, estimate sequence on the Riemannian manifold. So great, we show that with properly chosen parameters, our algorithm can construct a valid estimate sequence on Riemannian manifold. However, in order to achieve acceleration, we need to choose an alpha that is large enough. And we find it is necessary to assume a good initialization, which depends on the sectional curvature upper bound as well as the condition number. So, but note here that if the sectional curvature upper bound kappa goes to 0, we recover a global result which happens in the vector space. So in summary, we have the proof of Riemannian Nesterov's momentum method that at least accelerates locally on Riemannian manifolds, And we derive it using a new estimate sequence and a tangent space distance comparison theorem. There are many open problems remains, so if you are interested, definitely come by during the poster session. Thank you.
We have time for one question until the next speaker set up. Okay, I have a small question. So, do you know of any analysis for accelerated method over Riemannian manifold that is for non-convex objective that reaches some stationary point, which is faster than gradient descent, basically?
Yeah.
So, is there some? So. Does your analysis extend to these kind of settings as well?
Yeah, I'm not. So I'm not sure of that. Are they asymptotic results or are they?
Well, I'm asking if finite time, any better rate? There are better rates for non-manifolds, right?
Yeah. I think the trusted region method, they show some acceleration, but I think the assumptions are somewhat different.
Okay.
Yeah.
Okay, let's thank the speaker again.
Hey.
Okay.
Is it working?
Yes. Yeah.